application of support vector machine to Lassa fever diagnosis. I use this opportunity to say thank you to the organizers of the third International Conference on Artificial Intelligence and Logistic Engineering. I am Chinechere Omezwike, presenting on behalf of Wilson Wankwo, Wilfred Adigbe, Ijegwa David Achime, Chukwemeka Wankwo, Emmanuel Ojei, Duke Horody. Quality connotes fitness for purpose. And in healthcare, it entails correct and accurate diagnosis and prompt treatment of diagnosed diseases or cases. Quality healthcare is largely a function of right and accurate clinical decision making, which is done by the physician within the medical sphere. The amount of data amassed in the medical field is always enormous, unimaginable, and analyzing it to get correct diagnosis may be cumbersome. Machine learning and deep learning, which are technological trends applied to socioeconomic affairs, especially in the provision of quick and high precision prediction rules from historical data, have proven to be reliable and efficient. And when applied to the health sector, it will help specialists in diagnosis and making objective and reliable decisions. On the other hand, Lassa fever, an acute viral hemorrhagic disease with a cycle of between 2 and 21 days, was first discovered in northeast Nigeria in 1969. Lassa fever may be transmitted from human to human, which may often result in epidemics with case fatality as high as 60%. And in the early stages, it is difficult to diagnose it. Early symptoms of the disease are not specific, but may include the following: fever, sore throat, cough, headache, chest pain, abdominal pain, vomiting, to mention but a few. And it has late signs of infection as facial edema, bleeding, pleural, convulsion, to mention also but a few. Any disease with known symptoms is on its way to treatment and eradication. Now it is possible to develop and deploy a system that is capable of predicting the spread of the disease so that government agencies, medical experts, and individuals can take precautionary measures in fighting Lassa fever. This study aims to develop an intelligent diagnostic model for Lassa fever with specific objectives in designing a machine learning model that can serve as a decision support system for health experts in diagnosing Lassa fever. Secondly, implementing the designed model for the diagnosis of Lassa fever using the Python programming language. Methodology. Clinical data set was obtained from the epidemiological unit of a specialist hospital designated by the Nigerian government for the management and research on Lassa fever infections. The data set contains 1,728 records. Following the data cleaning, the data set was split into 80-20 ratio for training, testing, and evaluation purposes, as shown in the diagram below. Raw clinical data was obtained, was processed, and it was cleaned. And during the cleaning, we have the exploratory data analysis and the machine learning algorithm and model, which moves to communication, visualization, report, and findings, and finally build and deploy data product. There are some tasks that was performed. One was the data collection as I have already mentioned, but the data collected, they were unstructured with columns that are not required for training and testing. And some of these columns, such as the patient name and patient identity and home addresses, were expunged from the data set. The data sets that were used were named the useful features, and they are Lassa fever, which was a targeted variable, the fever, which was depicted by the body temperature, the body pain, headache, vomiting, jaundice, bleeding, age, and alcohol and cigarette intake. These were the useful features that were used for the machine learning model. During the stage of data processing, the raw data was transformed into a machine usable format, since the raw data contained incomplete and inconsistent values. The dataset was also labeled and encoded appropriately. The result of the resulting dataset was more reliable and fit for knowledge discovery. The input variable, which is the symptoms manifested by patients, the symptoms are transformed into two classes, the yes and the no, and the third class depending on the nature of the manifestation. While the target to predicted variable is a diagnosis of suspected Lassa fever, which is a binary classification. The input variable transformation are as follows. The Lassa fever, which is the targeted variable, has domain 1, which is yes and encoded 1, domain 2, no, which is 0, and when there is no presence of it, we have not applicable. Such is done for all the input variables, body pain, headache, vomiting, jaundice, gender, underlying health conditions. If there are underlying health conditions such as diabetes, hepatitis, high blood pressure, the domain 1 will be yes, encoded 1. Domain 2 will be no, if these particular variables are not available. And if there is nothing at all, it's encoded in the domain 3, which is not applicable. In every system, there are users, and this is depicted by the use case, which is used to represent a user interaction within the system. In this case, medical personnel, and the system is a system built for diagnosing Lassa fever disease. The use case diagram helps in understanding and identifying the operation and user's role in the entire system, as well as showing the relationship between the user and the designated functions. The designated functions are the loading of data set, exploring of statistics, fit and prediction with the support vector machine, doing the prediction result, analyzing and making decisions. And who does this? The medical personnel. The support vector machine is an algorithm that belongs to the family of supervised machine learning used for regression and classification problems. The support vector machine algorithm plots each data item as a point in a number of dimensional space, with the value of each feature represented by the value of a coordinate, and N refers to the number of features as I've mentioned in the data set. Thus, classification is performed by finding the hyperplane that most distinguishes the two classes. The study utilized the Lassa fever patient data set, which is in the form where the X is the feature and Y is multiplied by the number of data sets, which is the vector. Since there is a certain number of training data sets, given the training variable as X and output variable as Y, and defined by the two equations, equation 1 representing the training variable, while equation 2 is the output variable, where X in equation 1 belongs to a set of universal real numbers. This support vector machine algorithm is the function of Y and X that maximizes the error for all the learning features. Hence, the objective is to minimize the error, and to minimize the error where W is an n-dimensional vector representing the weight, which determines the trade-off between the differences in the decision function. The proposed evaluation, the result of this support vector machine model was evaluated by the prediction accuracy represented by a confusion matrix. Other evaluation matrices used include area under curve, receiver operating characteristics that evaluates the number of true positives against false positives. The data set comprises over 1,700 records of patients admitted for treatment of Lassa fever. And this is shown in figure 3 to 4, which as the summary and description of the data set in relation to the number of variables, Lassa fever case and not Lassa fever case respectively. This is also shown using a pie chart for more illustration, showing the percentage of distribution of Lassa fever. Where there is Lassa fever cases, we have 70%, and where there are no Lassa fever cases, we have 30%. Evaluation matrix to establish the efficiency of this model. Well-known and generally acceptable evaluation matrix were used. First, the prediction accuracy, and secondly, confusion matrix were considered. The area under the curve of the receiver operating characteristics evaluates the number of true positives against false positives, as I've mentioned before. This model is also evaluated with the precision and recall plots, and this is shown in figure 6. The confusion matrix, which is a productivity matrix for the problem of classification of machine learning, where 2 or more classes can be tested. It is a table comprising 4 different expected and actual value combinations. This is shown in figure 5 and table 3. As mentioned, this is the confusion matrix plot. The confusion matrix computation, where we have n representing the number, and we have actual, 0, actual, no, and the prediction. In the predictions, we have true negatives, 294, false positive, 69, false negative, 72, true positives, 84. The rates computed from the confusion matrix for the classifier model are presented in table 4, where accuracy has a value of 0.73, misclassification rate 0.27, true positive rate 0.86, false positive rate 0.19, true negative rate 0.81. Then precision is 0.55, prevalence 0.19, and recall 0.80. This is plotted in figure 6, the precision and recall. Clinical decision support and intelligence systems have a history of enhancing the efficiency of valuable socioeconomic workflows. In this work, we examine the applicability of support vector machine algorithms in the detection, diagnosis, and profiling of Lassa fever in patients using historical clinical data from a specialist hospital. The developed prediction model showed that valuable insights could be drawn from historical data and used to drive new diagnosis. The proposed system improves and encourages decision making in this regard and will be a valuable tool in the hands of medics who are saddled with the task of providing care for the helpless during Lassa fever outbreaks. The findings in this study, notwithstanding, recognize the limitation in the sense that the data set available was not detailed enough and also fall short of satisfying the adequacy metric in terms of the volume of data available. However, we believe that this study will constitute a good cornerstone for conducting future research in the construction of hybrid models that could provide better results for Lassa disease diagnosis and management. We acknowledge those who have done several works in this area of study, and by citing them and referencing them in our work. Thank you for listening.